Thank you very much. I'd like to thank the organizing committee for inviting me and giving an opportunity to speak on a topic that's near and dear to my heart. I've been in rare earths since 1995, and when I joined I couldn't spell them or even pronounce them, but things have come a long way. And as you pointed out, for the people that were there on Monday, as a Canadian, I have to apologize in advance for anything I say that may be inappropriate, because as a nation, Canadians just don't like to upset anyone. That's why we have the Americans to the south. Anyway, the one thing you need to know about rare earths, it's not a mining business. There are 260 projects, according to Jack, or companies on the Rare Earth Stock Exchange in Toronto, and they all come at it from a junior mining perspective. The reason being, it's easy to raise money as a junior mining company because the investment community understands mining. They don't understand the specialty chemical business, and it's very hard to get that point across. It was even more difficult in 1995 when people didn't even know what rare earths were. As I said on Monday, now every taxi driver you talk to can tell you all about rare earths, so the knowledge base has expanded quite rapidly. There is no simple way to sell rare earths either. There is no London Metal Exchange. It's not like copper, gold, silver, any of these metals that you can look up and see what a future price will be 6 or 12 months from now. Rare earths is a customized specialty chemical business. As I said, you sell to specific customers, specific quality and parameters. And the other thing is, processing is the key to success. There are many deposits in the world. I think I've heard as many as 400 under investigation right now. No two are the same. And that is the challenge in the industry. You have to go out and figure out how to metallurgically break down the deposit so that it can be beneficiated and separated. The applications, there's 4 main areas that we work in. Magnets, which Jack has touched on quite eloquently. Catalyst. I'll go into these in more detail in a minute. Glass and phosphors. There are 2 types of rare earth magnets. The first one was developed was samarium cobalt, and I think that was back in the 70s. It operates at higher temperatures. Most of the applications are military or specialty type applications that need to operate at an elevated temperature for a longer period of time. And the military is always willing to pay a little extra for the security. It's a steady but a small market overall. It was quite high in the 70s, but then the price of cobalt became very, very volatile, and people started looking for alternatives and came up with neodymium iron boron. And that was developed in the 80s. As I say, also samarium prices went quite ballistic. Samarium, the history of rare earths is that you end up piling up a pile of it on the side because there's no demand for it, and then somebody comes up with a great idea and all of a sudden the price goes through the roof. Samarium you used to be able to buy for $2 a kilo, then it went to $150. Now you can get it for $5 in the future. There's 2 types, sintered and bonded, and I won't go into it in great detail. The sintered magnet, if you have an iPhone, it will have a neodymium iron boron sintered magnet in there for vibration, or your BlackBerry or any of the other models. Apparently Samsung's the one we should be talking about now because they're now #1. The bonded magnet is a very interesting process. It's an injection molded magnet. Sintered is basically they make a large block out of it and they chop it into a specific size. The bonded magnet is basically an injection molded process where you can make the finished magnet to a accurate shape and size. And if you look at your hard disk drive motor, the small motors that drive your auto zoom, auto focus, and all your digital cameras, any of the small pieces of electronics that have a motor in it will use the bonded type magnet. It's as I say, small motors, electronics, wind turbines, and hybrid vehicles. J.D. Power estimates that by 2016 there will be over 3 million hybrid and electric cars in the world, and as Jack pointed out, that's not going to come even close to the internal combustion car, but the difference is each car uses 10 to 12 kilograms, so you're now looking at 30 million kilograms, or about 30,000 tons. Still a small number relative to what's going into the internal combustion engine, but it does have an impact on the overall. The nice thing about it is it has a compounded annual growth rate on NDFEB of 15 to 20%, and about the only dip in that straight line was 2009 and 2001, when basically we had two periods of where the world came to a halt for a short period of time. But once things came back to normal, you got this. And this is critical when you start, and I'll talk about it a little bit later, balance and rare earths. If you look at wind turbines, each megawatt is estimated to use about 400 kilograms of neodymium iron boron. That's from MCOA. And the world production is estimated to double between 2015 and 2030 from 249 gigawatts to 490 gigawatts. The nice thing about a neodymium iron boron magnet in a wind turbine is maintenance. The magnet doesn't have a lot of really moving parts. The other option is a gearbox, and when you have to go and replace a gearbox at the top of a 300-foot tower, it's expensive and it's a pain. So there is an opportunity for growth in the neodymium iron boron magnet for that market. Again, it comes down to economics and going forward. Phosphor market. CFL is compact fluorescence. If you look up at these light bulbs, they're all the low energy type light bulbs. And CRT, the old TV screens that we used to like that were about half a meter thick, LEDs and LCDs, they all use rare earth phosphors. Yttrium europium produces the red color, and the percent europium varies depending on the country you're in. Japan likes a different, more whiter color, so they tend to have a higher percentage of europium, 6.5, 7, 8%. Some of the other countries like a yellow or a softer color, so they use a little bit lower percentage of europium. But again, each one of these is customized to the end user. You don't do one size fits all in yttrium europium. The other one is lanthanum cerium terbium, which produces the green color, and then the blue is zinc sulfide, I believe. So you have the three primary colors that end up giving you white light. This is interesting. There used to be a lot of factories around the world producing light bulbs, and slowly over the past decade or so, most of that production has moved to China. As you can see, it's about 80% of the world's production right now. The main reason most of the people went there, two things: cost, but also security of supply. They need to be guaranteed that they can get their hands on the raw materials that are critical to them, and rare earths is one of those key components. Catalyst market, three main areas. All the new cars that come out have a catalytic converter on it. This technology was developed by, I believe, Engelhardt back in the 70s when automobile people really didn't pay a lot of attention to exhausts, and they now use a combination. In the early days, the catalytic converter used to be at the back end of the car, so it didn't have to operate at very high temperatures, and there wasn't at that time a monitoring process that you had a 15-30 second delay before you started actually checking what was coming out of the exhaust. As people got smarter and tighter controls came in place, the catalyst had to come up to operating temperature a lot faster. And to do that, you had to move the catalyst very close to the engine. The operating temperatures became much higher, so instead of using straight cerium, they started using a combination of ceria zirconia. Cerium is very nice. It changes valence. It's one of the few elements that can do that. So if you're running in a lean atmosphere where there's excess oxygen, it'll pick up the oxygen. When the engine moves into a rich or fuel-rich mode, it then releases the oxygen, and that way it helps with the aid of some of the precious metals, palladium, platinum, rhodium, be able to convert the NOx and CO2 to more appropriate materials. FCC, that's fluid cracking catalyst. It's used in petroleum to break down the barrel of oil that comes into the different fractions. Lanthanum is the main use here, and historically FCC has been about 70% of the world's demand for lanthanum. And then styrene, production of styrene uses a cerium-based catalyst. New opportunities that are coming up. Oh, dropped one slide. Glass. Glass, there's cerium is used for polishing. Up until this time last year, cerium was $5 a kilogram. Nobody paid any attention to it. It was basically use it, throw it out, forget about it. All of a sudden, cerium became $150 a kilogram. People started to pay attention. The consumption of cerium dropped by 65% last year because of that price impact. The other use in glass is lanthanum. For people like me who are not quite legally blind, but have an astigmatism, you end up with Coke bottle bottom glasses, lenses, when I was young. Now you can get, with the aid of lanthanum, a very, very thin glass. And that's, for people like me, a godsend. And then the other part is you can use gadolinium in lenses for HD, TV, digital camera, for TVs, TV camera lenses. And the new opportunities, Professor Yan is likely better equipped to discuss when this will ever come to fruition. People have been talking about gadolinium for magnetic refrigeration. It offers a lot of energy efficiency and hope, but it has yet to be commercialized and has been coming to market for the past 10 years. Another area is recycling. As I say, when I started selling rares in 1995, recycling wasn't an issue because there was lots of it available and the price wasn't that important. In the past 2 years, when we started seeing dysprosium go from a few $100s a kilogram to $1,500 a kilogram, it made people sit up and take a look and think it's worthwhile. So there are active programs right now in Europe. They're collecting all the old long tube fluorescent bulbs and even the compact fluorescents, and I believe Rhodia is looking to reactivate their plant in France just to process some of this material so that it doesn't go into landfill, and it at today's prices makes it worthwhile. Magnets. This will take a little bit longer. Japan is actively going at it, but you're not going to take the magnet out of your BlackBerry and recycle it. As Jack pointed out, for gallium, it's just not worth the effort unless neodymium prices go extremely high. But in the wind turbine and hybrid vehicles, the batteries and the magnets inside the braking system and so forth are big enough that it makes it easy to pull out and recycle. Japan, because they are deathly afraid of the death grip of China on them for rare supply, is very active in this area right now. and they're also looking at setting up plants outside of China. Just as a general overview of the rare earth market, China produces 97% of rare earths around the world. There's only currently one operational factory outside of China. It's in Estonia, in the Baltic region. It has the capacity to produce about 3,000 tons. It runs at about 1,000 tons a year because it just can't get the feed from the mine in North Russia. When the Soviet Union existed, they had a mine in the Kola Peninsula up near Murmansk. They had a processing facility in the Ural Mountains and to process the ore, and then they did the separation in Estonia. When the Soviet military runs your logistics, cost really doesn't matter. Now that these are three independent countries, everybody is an entrepreneur and they want to make money, it makes it a little bit more difficult. As I say earlier, 200 companies plus are pursuing projects around the world. This has been a very recent phenomenon. 5 years ago, most of these people were ABC Uranium Company because uranium was a very hot topic. Then all of a sudden it became very easy to raise money if you had ABC Rare Earth Company. So all of a sudden the uranium companies overnight became rare earth companies. And it's just, if you can get money, go for it. In the world right now, Lynas and Molycorp are the most advanced. They're closest to the finish line. The rare earth business is a horse race right now. 5 or 6 at top outside of China will get to the finish line. But you are in Malaysia really on the last furlong of the horse race right now. Molycorp, a little bit longer to go. There's a lot of questions still surrounding Molycorp. They've bought Silmet in Estonia. The common belief was that would give them some technology input. The problem is the technology in Estonia is not the same as the technology that they're going to run in Molycorp. Estonia runs on nitric acid. Molycorp will run hydrochloric. The Chinese have become masters of using hydrochloric acid in rare earth separation. So that's why they just went out and are proposing to buy the company I used to work for $1.3 billion. One, it gives them cash flow very quickly, but two, it gives them immediate access to Chinese rare earth engineers. You can graduate in China with a rare earth degree in chemistry. The only place in the world up until I get, hopefully UMP will allow you to do that. But it's, you know, it is a very important thing. As Jack pointed out earlier, the knowledge base outside of China and rare earths has evaporated, and it's a real missing link for industry in general. Not to say that the work in China is fantastic. They really know their stuff. But the Chinese government may not want to share all of that information around the world. And why would you? You know, so from that standpoint, being able to do projects at UMP to expand that knowledge base, in my mind, is quite useful. The other thing, as said earlier, not all rare earth deposits are created equal. There's lights and there's heavies. Lynas and Molycorp are lights deposits. They're basically bastnasite, 50% cerium, 25% lanthanum, 15% neodymium plus or minus, and 5% praseodymium, and then a little bit of samarium, europium, gadolinium. Not a lot after the gadolinium side. There are a lot of people now looking around the world at, quote, heavy deposits. Problem is, none of these deposits have ever been put into commercial production. And it's one thing people talk about, well, we've done a lab test and we can do it. You can do anything in a lab. It's amazing the reaction that you can get in the test tube. I did a research project on oxygen separation. We got tremendous results in a tube that was about 5 centimeters in diameter. I then went out and we built something that was close to 3 meters in diameter, and the whole process changed. So, you know, what you see in the lab isn't necessarily what you're going to see in the factory, and that's the thing. The scale up and the ability to run pilot, like some of the equipment we saw yesterday at UMP, is very critical, because if you're going to spend $300, $400, $500 million, you better hope it works, because that's a very large lab experiment to put in the ground. Key issues in rare earths. I'm obviously preaching to the choir here, but management of thorium and uranium waste is important. It can be done very easily. From what we saw yesterday at Linus, they have done what I consider leading edge technology in management of rare earth waste. I have seen plants in China, I've seen plants in Japan, I've seen plants in France. Nothing comes close to what we saw yesterday from that matter. Balance. Problem with rare earths is Mother Nature never really built a deposit in a ratio of rare earths that you can sell properly. You know, if you, right now, neodymium iron boron magnet is the driving growth, as say 15–20% per year. Problem is, if you separate one molecule of neodymium in bastnasite, you get 3 molecules of cerium and 1.5 molecules of lanthanum. You really don't have customers that buy in that ratio. So the trick is, especially in a heavies deposit, you try and sell all your yttrium, terbium, dysprosium, neodymium, praseodymium, hopefully your europium. Anything that you get for cerium and lanthanum is a bonus. The rest, basically, there isn't a market for, other than lutetium a little bit. So you throw them back in the ground. And the history of rare earths has been that every decade somebody comes up with a new brilliant idea, and you go out and the stuff now, the plant starts to make money on stuff they used to throw in the ground. So the problem is right now, rare earths hasn't had a new major breakthrough in 25 years. So we're waiting. Maybe UMP can do that. If they can, it would be fantastic. As Professor Yan showed, China is a leader in separation technology. The other thing that people don't recognize, mining is 10% of the rare earth business. Separation, it's critical, especially if you're working on a new deposit. But where a lot of your value add comes in is when you precipitate and calcine the product, especially for high purity materials. Talking 4.9s, 4.95, 5.9s material that go into electronics. You can affect the particle size, the shape, the surface area, the impurity levels. Is critical. If you want to put lanthanum into glasses like mine, you have to get very low iron. Anyway, I better stop talking. This is just a quick demand forecast for 2020 from a Canadian company called Byron Capital. The one thing that you note is that the supply in 2020, which is about twice the current supply rate, neodymium will only be produced at 30 to 35,000 tons. The world will want 50% more than that. So that then becomes the bottleneck. What technologies will advance forward and what won't, and at what price. Most of the others will be in dysprosium, will likely be in balance. All the others, particularly cerium, will be grossly oversupplied. So that's why, in my mind, over the next 5–10 years, the prices of cerium and lanthanum will go back to their traditional levels of $2, $3, $4 a kilogram. Implications, as I said, light rare earths over. We need more work on heavy rare earth deposits, and pricing in cerium will go down. Chinese advantages. Just so you know, the mine in North China is not a rare earth mine. It's an iron ore mine. And people get this confused all the time. The deposit is 80% iron ore, 20% rare earth. You mine it to get the iron ore out. They use all of the iron ore, but of that 20% that's rare earths, they only use about 1/3 of that to actually process. The rest goes back into tailings. So they have tons of that material available. In heavies, only South China is producing heavy rare earths, and from my definition that's basically terbium, dysprosium on down to the periodic table. And the other advantage, so China will still maintain their dominance over the next 5 years because there's no project that will hit the street in the foreseeable future. As I said earlier, they understand rare earth separation better than anybody. They moved from nitric acid to hydrochloric acid for a number of reasons. One is nitric acid is expensive. It's not that easy to find. In China, hydrochloric acid is coming out of everywhere to make PVC. The nice thing about hydrochloric acid is you don't need special materials. Every nitric acid plant in the world runs on stainless steel. Finding, in my own personal experience, finding good stainless steel in China in the early 90s was very difficult. They would say, I'll give you low carbon steel, but it's going to have this extra. No, that's not stainless steel. That's just a nice steel with some other elements in it. So they moved to hydrochloric acid for cost reasons, but also because they could build their separation cells out of PVC. The plants that we saw, the plant we saw yesterday, your separation cells are made out of fiberglass, locally in Malaysia. They look brilliant. Very well designed, well thought out. But again, stainless steel versus PVC or fiberglass, there's no comparison. Just somebody asked me about Canadian mining law. I don't think you really have to worry about it. There's a section we call 43-101, and that was brought in because of a Canadian company that did a bit of a scam in Indonesia 20-odd years ago called Briax, where they salted the gold mine samples, and now to start mining in Canada and go and sell on the public market, you basically have to go through this. It's to protect the investors. You have to have a third party go in, but you also, I won't go through all of this, but one of the key things is the environmental studies and waste and tailings disposal. All of this has to be laid out in advance. And just briefly summarize a review of what we saw yesterday. It's a world-class facility. As I say, I've seen plants around the world. There's nothing that, other than the one in France, but that was built 30, 40 years ago. The technology that's being used in this facility is the best that you can buy when that plant was designed, without a doubt. They've spent a lot of time, money, and effort to understand, address, and develop facts. And to me, I should have put an underline under that. It's a fact-based argument. They went through 23 different issues and concerns that have been raised within the country and came up with factual information on each one of those 23. You know, you can't argue against somebody's perception if they don't want to listen to the facts. You know, that's their choice. But as engineers and scientists, we can only deal with stuff that you can put a box around. You know, and in my mind, they've done everything that they've spent millions of ringgit just trying to understand the concerns and get tests done around the world to prove that this operation is safe. And the other thing is, people said, well, why didn't he go and stay in Australia? They had a permit to build a plant in Australia. The problem is, and I can address the question later, I have the specific numbers. This plant uses 500 cubic meters an hour of water. That's a lot of water. Perth doesn't have a lot of water, unless you want to bring it from the ocean. So that to them was a critical factor. And their power, I can give you the specifics in a minute when I sit down, significantly different. You know, labor is not a major cost in rare earth separation. It's a 5%, 10% of the total cost of an operation. 50% of your cost is your raw materials. And then you have your operational costs, power, water, and so forth. So, you know, they didn't come here for cheap labor. They came here for skilled labor, yes. But cheap, no. That doesn't drive a rare earth plant. Oops. And finally, opportunities for Malaysia, as we think every one of the members here has talked about, become a world-class producer, but also being an alternative site to China for downstream plants, as Jack said, Bose. Bose is the end of the food chain. You need somebody in between to actually make the magnets, but the Japanese have shifted a lot of technology into China over the past decade because they wanted to be close to supply, because they can't run their plants without it. With the operational facility here in Linus, you can do the same thing. Molycorp is talking about doing the same thing in the US to go into magnet production and so forth. And I won't go through this because I'm basically reiterating what everybody before me has said. Thank you very much.
Thank you.
When you hear Alastair talk like a scientist, he has an engineering background. But unlike myself, who stuck to engineering, Jack and Alastair, they abandoned engineering but use engineering know-how to go into a niche market of a rare earth industry. And as Jack just mentioned, he doesn't worry about money anymore. I still have to worry about money. So for the young engineers here, for old engineers like me, there's no more hope. For young engineers, right, use your engineering experience and your knowledge. Go into some niche area with develop your entrepreneurial skill, and then become tycoons like Alastair and Jack.
I'm still worried about money.
No, you are worried about making more money. Yeah. So anyway, can I open the floor for Alastair? Any questions that you want to pose to him? No? No one want to make money? Ask him about that. That making money, so whenever we say that, look at somebody else making money, you think that that is an easy area. Until you put your foot into that, and if you are not careful, you put 2 feet there and you sink without trace. But anyway, any question? Yeah, Rob?
I'm Azur from UNP. Just like to reiterate what Alastair said about the scale up. I think scale up is very important, especially in the city of Malaysia, because we have a lot of research in basic research in the grand scale. But when we go to the commercial, we need to scale up. That's why UNP would like to concentrate on the scale up. I think from the beginning when we established, we want to concentrate on the scale up of the processor. But I would like to know maybe from Alastair and maybe from Prof. In the case of rare earth processing, I think, are there any more opportunities for scale up? I think, is there some areas that we can concentrate on the scale up issue?
Okay. They're running 11,000 ton per year trains. Most of the factories in China, and Professor Yang can speak this better than I, run 5,000 or 6,000 maximum. So they're already sort of breaking ground in that area. Molycorp is looking to do 20,000 ton a year trains, which has never been done. 6 to 11, that's one thing. 6 to 20 as a whole, because as we all know, your kinetics, your mixing, the flow dynamics within the cells and so forth are completely different. I don't know how you scale that up without actually building a full-scale cell and see what happens, because I used to work for a company called Union Carbide Industrial Gases, and we had a process which was a graphite tube in a furnace spinning with argon going down it to make very small bubbles. And the only way that they could actually figure out whether this thing would work or not was build a full-scale plexiglass mock-up of the system without the temperature, obviously. But you could see through the plexiglass what was going on with the bubbles and so forth. Unfortunately, it mimicked the the application in aluminum quite well. So yeah, I agree. Scale up. Sometimes the only way to do it is actually build one and see what happens.
So what we're thinking of right now is about scale up. I think can do in two parts. One on the experimental into the pilot plant, or the other one it might be on the simulation. I think there's a lot of opportunities in simulation once we understand about the properties and also about the capability of computing.
Yeah, I think the other thing that's the current generation has that I never had, or Jack or any of us really, is you've got computer simulation, which is a very powerful tool. You know, coming from the slide rule generation, that just wasn't an option. And you know, computer simulation can answer a number of those questions, I think, in advance.
When we were at the plant, we drove by a building at least the size of this room. And I said, what's that? He said, well, that's our computer management center. He says, of course, we're looking for new tech. We've got the best company in the world on program management of chemical plants. And I said, so he said, well, it works, but we want to do better. What worked was something even 30 years ago would have been all the computers for a nation. And so this is happening also. And as you know, it's much easier to be a programming specialist in computer science. You need a pencil and a pen and paper and a laptop. So this is an opportunity for people who are mathematically literate, like people in Malaysia. It's a real opportunity. Right.
I've got one last point.
Okay, please.
One thing that's of interest when you walk around or look at the Lions plant or any rare separation plant, there's a lot of liquid in the cells and there's a lot of money in the cells. Like they have over $2 million worth of rare stuff in the cells that they can't get out because it's a continuous flow through the process. You know, I looked at ion exchange, and that only made sense for something like lutetium at the time, which was $3,000 a kilogram. You know, looking at alternative ways to do it other than the current liquid solvent extraction route to reduce the work in process and the volume of liquids involved would be a godsend to the industry because, as I say, when prices went from $2 a kilogram to $50 a kilogram, all of a sudden they had 24 or 25 times more money stuck in the plant. And that hits your balance sheet. There's nothing you can do to get it out. So that's an area, personally for me, that would be of interest in future plant design.
Anyone else? Okay, please come to the front with the
Just asking about viability and sustainability of the business process. Viability and sustainability of the business. I'm not talking about technological advancement because there's a lot of things to learn. But the probability of survival of this particular industry, especially when compared to China, as a big market, we supply about 97% of the rare earth globally. I'm also talking about the market pricing. From $2 per kilo, increase of 100 kilo, I mean the 150 kilo. I mean the pricing is changing very fast, yeah. And the change of technology is also very fast. Can this industry sustain when we try to compete with China in the real world? In terms of customer, they need China to change the pricing. Because of the cost of investment is cheaper in China, can the industry sustain?
Okay.
Yeah, if you'd asked me that question 10 years ago, I would have said no. Because the industry was completely fractured inside China, and they would cut, their idea was economically to drop the price and get the production in the plant up so that they could build a bigger plant, get lower unit cost of production, and drive their competitors out of business. The reality of the situation is you don't drive your competitor out of business in China, they just stay there and don't go away. But you know, the industry inside China has gone through a major restructuring. Instead of 150 or 200 companies in the business, now you have 5 state-owned enterprises. The government has also recognized that there is an environmental cost and that there is a price to be paid for that, both in human terms but also economically, so that they have to put the proper systems in place, and those don't come free. We put a wastewater treatment plant into our factory near Shanghai. It cost $1 million. Nobody gives you anything for that, so you have to recapture that money somehow, and that's through the price of the material. And the prices in the late 90s, early turn of the century got to a point where it wasn't economically sustainable. What happened last year was a bubble, there's no question. That was a lot of speculation, a lot of fear going on. Prices are retreating, but again, the thing you have to look at in rare earths is it's not a lump. It's 15 different elements, 15 different markets, 15 different demand and supply situations. And it comes back to the balance. Neodymium and praseodymium will be critical. I think Jack did some quick math. And you know, Linus alone, just on neodymium, will make revenues of $400 million a year. That can sustain a lot going forward. So from that standpoint, yeah, I think it is sustainable. Well, you know, somebody asked me what would China do, and my point is, after 17 years in China, if I even venture to guess what China would do, I'm an idiot, because you can't really predict. But I think they'll keep things where they are in general.
Can I just add a final comment about the Chinese supply? We keep on hearing about the 97% or 95% of world supply. If they continue to do that, then they would not have been that the US, Europe, and Japan took them to the WTO. It is because the export is actually less and less as they use the rare earth, you know, domestically for the downstream industry, the green, you know, like wind turbine, for example. Within a very short time, they overtook Denmark, they overtook Germany as the figures. So the world supply from China, actually, it is getting less and less. And the Chinese argument is very simple. We have 40% of the world's resource or reserve in rare earth. Why should we continue to supply the world 97 or 95%? So, as it was mentioned today, so minus Malaysia would become the second, you know, to China, the world supply. And my interaction with the Chinese is that they do not like this monopolistic position in rare earth because they are under attack for political reason, not for scientific or even economic reason. But now it's an election year in America, and this is an issue that is tinged with politics. China bashing, including rare earth, is, you know, now the flavor of the month. So I think the question about China is that they will be dominant in the supply, but more importantly in technology. But they will be also dominant in future in the downstream green and clean industries. Okay. So before I move on to the next speaker, can I ask you to join me in thanking Alastair?